All right, so we've been studying subspaces, and we saw that in R2 and R3, some of the basic examples of subspaces are lines through the origin and planes through the origin. For these examples, we have some intuitive idea of the notion of dimension. For example, we would say that a line is one-dimensional, and a plane is two-dimensional. And actually, we can add another example because Rn is always a subspace of itself. And we would think of Rn as being n-dimensional. But in math, you need the definitions to be precise. And there's this issue that when we say, for example, that a line is one-dimensional, what do we actually mean about that? All we really have at this point is intuition. Well, we're finally ready to make such a precise definition. But before I do that, I would like you to pause for a second and see if you can just guess what the definition is. Think about the things that we've been studying recently and how your intuition for dimension fits in with those things. All right, are you ready? The dimension of a subspace W is the number of elements in a basis of W. Okay, so if somebody just gives you a mathematical definition like this, I'd say that in general there are three sorts of questions that you would want to ask about that. The first is more of a conceptual question. Is this the definition that we're looking for? As in, does this definition actually convey the intuitive idea of dimension which we already had? And luckily it does. For example, if you have a line through the origin, then you can take any non-zero vector on that line, and that will give you a one-element basis for the line. So this definition would tell us that the line is one-dimensional. And if you have a plane through the origin, or at least in 3 dimensions where you can visualize the picture, you probably should be willing to believe that you could pick any 2 linearly independent vectors on that plane, and those vectors would provide a basis for the entire plane. And so that's a basis with 2 elements, and so according to this definition, the plane would count as being 2-dimensional. And then for Rn, we actually have these standard vectors, e1 to en, which span all of Rn, because every vector can be written as a linear combination of these vectors, and which is linearly independent because none of these vectors can be written as a linear combination of the others. So according to the definition, Rn is n-dimensional. So this is good. This means that, to the extent that we had some intuition for what dimension means, this definition that we came up with agrees with that intuition. So a second thing that you would want to ask is more of a theoretical issue. Is the definition well defined? And what I mean by that is it unambiguous? So what could go wrong is that in this case, in order to say what the dimension of a subspace is, you need to have a basis, and then you count the number of elements of that basis. But we know that there are different bases for any given subspace. So basis is not unique. Is it possible that there are 2 different bases for one subspace where the number of elements is different? If so, then that would be a problem, because one basis would tell you that the dimension is one number, and then another basis would tell you that the dimension is another number, and that would make it ambiguous. Well, luckily there's a theorem that says that every basis for a particular subspace W has the same number of elements. So the dimension is unambiguously defined. Now this is a theorem that we're not going to prove right now. It's not obvious at all, and it's actually not super simple. There's a proof in the book, and Brecher even says in that proof that the proof is rather technical and not very illuminating. But we will give a proof later once we have better tools for understanding how it works. For now, you can just take it for granted. And then the third thing that you might ask about this definition is, can we actually use it to calculate the dimension of a subspace? And for practical purposes, the answer is yes, because the subspaces that we actually encounter in real life are basically always either images or kernels or spans of vectors. And we know how to find bases for images and kernels and spans of vectors. And once you know how to find a basis, then you actually know how to find the dimension, because that's just the number of elements in the basis. So let's look at an example. Here's a matrix A, and the question would be to find bases for the image of A and the kernel of A, and then to find the dimension of the image of A and the kernel of A. So for both of them, the first step is to put A in reduced echelon form. And so here is the reduced echelon form according to Wolfram alpha. And from this, the first thing, the easiest thing for us to do, is to find a basis for the image of A. And to do that, we look at where the pivots are. There are 3 of them. And we just take the vectors that are in the columns of A in the same spots where the pivots are. And so this is your basis for A. The second and fourth columns of A are redundant because they can be expressed as linear combinations of the basis vectors. And in this case, you can actually see that from the reduced echelon form. The fact that the second column in the reduced echelon form is 2 times the first column corresponds to the same relationship in A, that the second column of A is 2 times the first column of A. And even though it takes some calculation to double check, the relationship for the fourth column that we see from looking at the reduced echelon form is that the fourth column is 5 times the first column minus the third column. Check that it's true using the columns of A, that the fourth column of A is 5 times the first column minus 1 times the third column. So now, what's the dimension of the image of A? Well, there are 3 vectors in the basis, so the dimension is 3. That's it. Now, because this comes up quite a bit, where you're asking about the dimension of the image of a matrix or a linear transformation, there's a special term for it, and that term is rank. So we would say that the rank of A is 3 in this case. Now, can you think of a quick way to just look at the reduced echelon form and see what the rank is without really thinking at all? And yeah, it's just the number of pivots. Remember that every pivot corresponded to a basis vector in the image of A. And so the number of pivots is going to be the dimension. It's going to be the number of basis vectors. Okay, so now let's move on to the kernel. For the kernel, you have to do a little bit more work. You write out the reduced echelon form as a system of equations, and then you observe that because there aren't pivots in columns 2 and 4, those correspond to free variables. So x2 and x4 would be free variables. So if we set x2 to be s and x4 to be t, then we can solve for x1, x3, and x5. And we get x1 is minus 2s minus 5t, x3 is t, and x5 was already 0. So we collect the equations for x1, x2, x3, x4, and x5 together into a single vector, and then we can split this vector into 2 terms, one term that has an s in front of it, and another term that has a t in front of it. So when we write the solution this way, we're actually expressing the kernel of A as the span of 2 vectors. And those vectors will automatically be linearly independent. It's actually worth thinking about why those vectors are always linearly independent. We never formally proved it, but there's a fairly simple explanation for it, and I think it's a good exercise for you to think about why. But anyway, this means that we have a basis for the kernel of A consisting of 2 vectors. And so that means that the dimension of the kernel of A is 2. Now the dimension of the kernel of A also has a special name, and that name is nullity. So in this case, the nullity of A is 2. Now can you think of a quick way that we could just look at the reduced echelon form of A and figure out what the nullity is? Well, yeah, there is something. So you notice that when we solved for the kernel of A, we sort of automatically solved for it as a linear combination of vectors. And each of those vectors corresponded to one of the free variables. The free variables are the coefficients that are being multiplied times the basis vectors. So the number of vectors in the basis for the kernel of A is exactly the same as the number of free variables. And that's a general principle. That's something that's always true for any matrix. So this is cool. We've actually found a quick way to figure out what the rank of A is and to find out what the nullity of A is just by looking at the pivots in the reduced echelon form of A. And in fact, there's something more here that's really interesting. These 2 numbers are related to each other in a way. The rank of A is the number of pivots in the reduced echelon form of A, and the nullity of A is the number of free variables in the reduced echelon form of A. And where do we see the free variables? Those are the columns that don't have pivots. And so when you add those two numbers together, you just get the total number of columns, because you're literally adding the number of columns that don't have pivots to the number of columns that do have pivots. And that's going to give you the total number of columns. Yeah, that's right. You thought I was just showing you an example, but I was proving a theorem. It's called the rank nullity theorem, and it says exactly what we just saw. For every matrix A, the rank of A plus the nullity of A is equal to the number of columns of A. So this is kind of a big theorem, but I'll admit that at this point you might not be able to appreciate it that well. It's something that you notice is true for any matrix, but you might wonder how you would actually use it to learn something that you didn't already know. And so this is something that we'll see later on when we're working in a more general framework. But basically the idea is that you could be in a situation where you don't know what the rank is directly, but you know what the number of columns is, and you know what the nullity is, and then you can use that to figure out what the rank is. Or on the other hand, maybe you know what the rank is and the number of columns, and you use that to figure out what the nullity is. But for now, I think it could be good to give an interpretation of this in terms of linear transformations. So suppose we're in a situation like this where we have a linear transformation from R3 to R2. Then the matrix that corresponds to this linear transformation would have 3 columns and 2 rows. So the number of columns of A would be 3. That is exactly the dimension of the domain, and I would say that that's the right way of thinking about why that number is there. It's the dimension of the domain. So what does a linear transformation do? It takes all of the vectors in the domain and it maps them over into their image. So we know that the image is a subspace. In this case, if it's a subspace of R2, it's either going to be just the 0 vector or a line through the origin or all of R2. So let's just say it's a line through the origin. Well, if that's the case, then the rank of A would be 1 because the line through the origin is one-dimensional. So geometrically, we are talking about the dimension of the image. So then we have to think about, how is it possible that we started with a 3-dimensional domain and we ended up, after transforming all the vectors, we ended up with a 1-dimensional image? How is that possible? Well, in order to make that happen, this transformation would have to collapse 3-dimensional space down into a 1-dimensional line. And in doing so, you would be collapsing it down by 2 dimensions. And I'd say that that is the right way to think about what the nullity measures in terms of the geometry of the problem. The nullity is basically measuring how much collapsing is going on when you perform the linear transformation. How many dimensions are being collapsed down? All right, I think that's everything to say about this. See you later.